Since times of old, navigation has always required high levels of both knowledge and skill. On the high seas for long periods of time, modern officers must demonstrate proper understanding of maritime conditions and ship mechanics, as well as a mastery of sophisticated modern navigational instruments. This video is designed to help you understand how to use navigational instruments. We're confident that you will find this video interesting and easy to understand, because you have already encountered these instruments on board your ship. It's recommended that you read the operating manuals for your particular vessel's instruments before working with them. This new standard applies to all such radars fitted after July 1st, 2008. What is known as the radar image is displayed in the center of the screen. Look at the upper left-hand side of the screen. Here, information such as the range scale settings, motion display mode, and azimuth display mode are shown. On the lower left-hand side of the screen, the gain, STC, FTC and the tracking mode settings are displayed. On the upper right-hand side of the screen, information on the position and bearing mode of the cursor mark, relative bearing, true bearing and the off-center mode are displayed. On the lower right-hand side of the screen, the EBL direction and bearing mode and the VRM distance are displayed. Finally, on the far right-hand side of the screen, the speed, course and position of your own ship are shown. It's also possible to display information on any number of acquired target ships. To change from the relative mode, RM, to true mode, TM, left-click RM at the upper left-hand side of the screen. As the mode changes to TM, the own ship position is offset in a direction opposite of the own ship's course. Stationary targets like land are fixed on the screen, whereas the own ship position moves according to its speed, heading, and the effects of wind and current. As the own ship position reaches the center of the screen, it's reset to the direction opposite of the own ship course, after taking into account the effects of present wind conditions. Select one of the available azimuth modes to display the radar image you desire. The North Up display positions north at the top of the screen. Note that in this mode, fixed targets do not move, making it easy to compare the display with charts of the area and read the true azimuth of a distant target at a glance. When switched to the head-up display, the heading is shown at the top of the screen, that is 0 degrees on the fixed azimuth circle. Fixed targets are displayed in the direction owned ship is heading, providing the same range of vision as seen from the bridge of owned ship, making this setting suitable for lookout duty. Head-up mode cannot be selected when the instrument is in true motion mode. In the course-up mode, owned ship's course is positioned at the top of the screen. As with the true azimuth display, fixed targets are displayed without stagger, even if owned ship is yawing. Also, the direction of the ship's heading moves only when a change is made in owned ship's course. To change course, select Course Up mode by pressing the azimuth mode button several times. Before operating a navigational radar, confirm that all basic data from the requisite onboard instruments have been input. Data items include GPS and gyro compass data, owned ship speed, and AIS information. The range scale can be changed to suit the navigational requirement. Gain, tuning, brilliance, sea and rain anti-clutter levels are changed by pressing their switches. It's important to obtain needed information by adjusting the STC to obtain the best radar image in various sea states. Normally, these functions operate automatically. Adjusting the sea clutter knob allows you to understand the state of the sea and determine sea wave propagation directions. The two functions, EBL and VRM, are used to measure bearing and distance. Here we'll explain the measurement of bearing and distance between owned ship and the target, and between 2 points on the radar display using EBL and VRM. Select EBL1 or EBL2. Next, select Off-Center. Set the EBL origin to one of the targets, and set the outside edge of EBL and VRM to the other target. If owned ship is drifting off the set course, it's easy to determine the influence of sea currents and winds by placing a cursor line parallel to the heading line of owned ship at a safe distance from a conspicuous target, like a steep headland, the tip of a breakwater, an isolated rock or islet. Use of a parallel index line is also effective for maintaining a safe distance from the coastline when owned ship is coasting. Indicate the line of parallel index. Set the line to the heading of owned ship using the electronic cursor knob and EBL knob. Use the variable range marker and EBL knob to adjust the parallel line interval and set the line on the target. Whenever the target slips off the parallel index line, the course of owned ship should be adjusted. The trail's length is a record of the past position and speed of the other target ship, which is useful for collision avoidance. Trail's length has 4 settings, from a minimum 0.5 minutes ago to a maximum 6 minutes ago. Up to 20 marks can be displayed. Maintaining waypoints with longitude and latitude marks can be used to indicate anchoring points or course altering points. Picking up a target is done manually. While the vector length shows the target's past speed, it can be changed to a suitable length for easy display depending on the situation. The target's past speed and direction can be checked visually, making it possible to estimate course and degree of collision risk. ARPA displays the movement, course and speed of targets by radar image analysis to determine the risk of each. It's necessary to use either the relative vector mode or true vector mode from the viewpoints of collision risk estimation and collision avoidance. The relative vector display mode can be used to find the closest point of approach, CPA, and time of closest point of approach, TCPA. This enables the relative vector display mode to keep under observation all nearby ships that pose a collision danger. The true vector display mode shows the speed and course of targets and the aspect angle between own ship and targets. As such, it's possible to grasp what's defined by the law for preventing collisions at sea as ships encounter situations. The relation between own ship and a crossing vessel, an overtaking vessel, one traveling in the same direction and one approaching. ARPA can capture and track up to 50 targets and display all dangerous situations, displaying each with a symbol and sounding an alarm. ARPA has a trial maneuver function. When a potential dangerous situation between own ship and other vessels is identified, ship handling for collision avoidance can be examined using trial maneuver. It's necessary to include sufficient distance in time in the minimum CPA and TCPA. Initial evasive distance must always be adequate. In periods of good visibility, get in the habit of comparing the radar image with what you actually see. This knowledge will help you grasp target movements using the radar display alone when navigating in poor visibility. Training that embraces a variety of circumstances is recommended. When a new target has been picked up, it may take 3 minutes or more for its vector to reach a prescribed accuracy. Also, if either the target vessel or own ship has changed course, it may take a few seconds for the vector to be rendered accurately. In true vector mode, the direction of the target's vector stands for its true course, while the vector length is proportionate to its speed. This makes it possible to correctly grasp movements of nearby vessels. A relative vector, meanwhile, does not represent the target's true movement, but simply shows a relative position between own ship and the target. In other words, if a vector points toward own ship, it should be considered a dangerous target. In relative vector mode, it's possible to grasp at a glance where the target's CPA limit is. The MSC 79, 79th Marine Safety Committee, has revised the performance standards for navigational radars. Note the following. The reference point for the measurement of a target's distance and bearing has been changed from the radar antenna position to CCRP, Consistent Common Reference Point. As a result, the position of the EBL and VRM is displayed as the distance and bearing from CCRP. Because the radar antenna position differs from the CCRP, the radar image appears off the center of the screen. The radar image's effective diameter has been reduced from 340 millimeters to 320 millimeters. It's now mandatory that the radar display indicates basic navigational information. The number of targets that can be acquired by the ARPA has been increased, and the number of targets that can be displayed by the AIS has also changed. Note that the functions formerly displayed in the ARPA have now become standard elements incorporated into the radar's new target tracking, TT, function. AIS, Automatic Identification System, has been developed to improve safety at sea, support safe and efficient navigation, and protection of the environment. Using the VHF band, the AIS periodically transmits navigational information, such as the position, speed, and course of own ship, the ship's name and cargo. It also continuously receives and displays similar information received from other ships. Under the SOLAS Convention, all passenger boats, ocean-going cargo ships over 300 gross tons, and coastal cargo ships over 500 gross tons are required to install AIS. Own ship data that is automatically entered and updated in the AIS include the ship's position from GPS, speed over the ground from log, and the heading from the gyro compass. Other data must be input manually. Before a voyage, the following navigational information should be input manually. For manual input of navigational status, choose from the following items: navigation status, destination, ETA, draft, cargo status, waypoints, waypoint text, persons on board, height over keel. Among the navigational status items for manual input are underway using engine, at anchor, not under command, the AIS can transmit and receive text messages to and from all vessels, and to and from specific individual vessels. It's possible to choose between safety message and routine work message, but the length of each is limited. AIS data can be output to AIS-compatible radars and ECDIS. Also, it can be output to other instruments using a pilot plug. AIS offers a collision avoidance support function, providing information that cannot be obtained with radar or ARPA. The benefits are as follows: real-time information updated at intervals of 2 to 10 seconds while navigating. Immediate updates of changes to target course. Elimination of target swapping. Target no longer hidden by sea and rain clutter. High-speed targets rendered accurately. Information can be obtained from a ship on the other side of an island or cape using VHF transmission. Reporting intervals for dynamic information data are as follows. Every 3 minutes when anchoring or mooring under 3 knots. Every 10 seconds when sailing under 14 knots. Every 3.3 seconds when sailing and altering course under 14 knots. Every 6 seconds when sailing between 14 and 23 knots. Every 2 seconds when sailing and altering course between 14 and 23 knots. And every 2 seconds when sailing over 23 knots. These intervals mean that course alterations made by other ships can be obtained in near real time. Data acquired by the ARPA function is updated with every radar scan. Updating generally takes several seconds and varies according to the radar scanner rotation interval, target vessel speed, turn rate, calculated ship speed, and so on. On the screen, the AIS and the ARPA vectors are superimposed, but not aligned. This is because the data processing methods are different. As the course of the target stabilizes after altering course, the two vectors will correspond. To use the information obtained for safe navigation, you must understand its acquisition method, processing method, and update intervals. The AIS automatically transmits and receives 4 kinds of information: static, dynamic, navigation, and safety-related messages. AIS information makes it possible to directly contact a target ship to confirm evasive ship handling. It's also possible to estimate a ship's course according to its destination. It's important to understand the operation and use of this equipment so that it may be used for safe, efficient navigation and protection of the marine environment. ECDIS, Electronic Chart Display and Information System, is a comprehensive information device for navigation. It meets the performance standards established by IMO and IHO. ECDIS displays an electronic chart based on official charts issued by each country's hydrographic department. Gyro compass data, log data, GPS data, the radar image, and AIS information are superimposed on it. When connected to an autopilot system, ECDIS allows automated navigation based on the voyage plan. ECDIS displays the electronic chart. Own ship information displayed includes the ship's symbol, position, speed, and course. Other ship information displayed includes ARPA and AIS information, such as bearing and distance from own ship, CPA, and TCPA. On the ECDIS display, it's possible to superimpose the radar image and perform both voyage planning and lookout. Unlike the autopilot, the system can keep the ship on a preset course. It also offers a stranding prevention function by issuing a warning when the ship is deviating from the set route or when it approaches the safety contour line. There are 2 types of electrical chart for ECDIS. The raster format chart is called an RNC, Reference Navigation Chart. Made by scanning paper charts produced by each country's hydrographic department, its digital data is updated regularly. When the chart is enlarged, letters and symbols are enlarged accordingly. The vector chart is called an ENC, Electronic Navigation Chart. It's issued by various governments' hydrographic departments or government agencies. Because this chart is recorded in a vector format, all details are displayed clearly even when the chart is enlarged. ENC uses the same geodetic coordinate, WGS84, World Geodetic System 1984, adopted for GPS. ECDIS is usually installed in large vessels with modern integrated bridges. However, because large vessels do not normally navigate coastal areas of the Pacific Ocean and Japan Sea, only 1 to 300,000 or smaller charts are available for these waters. Furthermore, some smaller ports do not appear on ENC charts. Because ENC doesn't cover every corner of the globe, paper and raster charts are essential. The update method is indispensable for safe navigation. Let's look at the update method based on CD-ROM. Insert a CD-ROM. Select Chart Portfolio from Tool, then select Create. When warning is indicated, press Yes. When a new window is opened, click Auto Detect and select Option. Select the type of chart you will import. Change Cell Permit to Import. When import is completed, click OK. Click Import Update and updating will start. The length of the updating process will depend on the number of charts stored in the ECDIS. As such, updating should be done during times of low activity. Here are some points to remember when using ECDIS. When the radar image is superimposed on the ECDIS, the coastline of ENC and that of the radar image do not necessarily match. A ship positioning alarm sounds when a signal from an electronic positioning system like GPS is intercepted. As an alternative means, ECDIS can use dead reckoning based on calculations from the gyro compass and log. A gyro compass determines true north based on gravity and the Earth's rotation. The output signal is sent to various parts of the ship for use with the autopilot system, the radar, the Inmarsat, and the AIS. The gyro compass's main function is to indicate true north and continuously output azimuth signals. Here we'll look at the method of starting and stopping the gyro compass and error correction. Let's consider gyro compasses from Japan's two leading manufacturers. With the gyro compass made by Yokogawa, when the main power switch is turned on, a rotor in the gyrosphere starts to turn. The repeater switch is turned on when the rotor is at full speed, and the phase current decreases to a preset value. The azimuth direction that all repeaters indicate will be the 0 degree position, and the master compass will then be adjusted to the 0 degree point. The azimuth direction signal sent to other equipment can be selected from among Gyro 1, Gyro 2, and external. Turning off the main power switch stops the system. For the gyro compass made by Tokyo Keiki, turn on the main power switch. Check the ship's position, latitude, and ship speed, then set the starting azimuth. If a discrepancy between the indication of the gyro compass and that of the repeater compass is discovered, adjust the repeater compass. Make adjustments using the knob on the side of the repeater compass. For the Yokogawa product, press the synchronization button. Gyro compasses are subject to latitude and velocity errors. These error margins are usually corrected automatically using GPS latitude and log speed signals. When automatic input is not available, or the input signal is known to be incorrect, switch to manual operation and make adjustments based on the correct data. The ship is constantly shaking due to rolling and pitching motion. This motion increases the gyro compass margin of error. One solution for this problem is to use 2 gyro rotors. One method of gyro compass error measurement is the amplitude method. The other is measurement using the azimuth of the ship's berth. Gyro compass errors should be measured at regular intervals and the measurements recorded. Because the autopilot is part of the overall steering system, understanding the autopilot means understanding the entire system. The steering system is composed of a steering stand in the bridge and a steering machine controller in the steering engine room. Given its vital importance, there are 2 completely separate control systems, enabling steering to be restored immediately should one of the systems break down. The steering signal is sent from the steering stand to the control and power box as a steering control signal. It controls the piston control unit of the hydraulic steering gear using oil pressure to move the rudder. Here we'll explain a model that employs a solenoid valve as the actuator. When the rudder moves, the rudder angle signal is transmitted to the control and power box via a mu transmitter. The solenoid valve is shut when the required rudder angle signal equals the rudder output signal, enabling the rudder to hold the prescribed rudder angle. There are 3 steering modes: manual, automatic, and non-follow-up steering. For manual steering, set the mode change switch to hand. This mode allows you to perform precisely controlled steering because you handle the steering wheel while looking at the rudder angle indicator. When entering or leaving port, or when navigating through a narrow channel, congested waters, or in poor visibility, switch from automatic to manual steering so that you can respond quickly to changing circumstances. For automatic steering, change the mode change switch to auto. This steering mode automatically maintains the preset course. It's suitable for use in safe and unconfined shipping lanes, away from the shore where there are fewer ships. Automatic steering makes it possible for watchkeepers to concentrate on lookout work from the bridge. Non-follow-up steering controls the rudder by directly controlling the power unit solenoid valves of the steering engine in the event both manual steering and automatic steering have failed. Even if both the automatic and manual steering systems break down, rudder control is possible as long as the steering engine is operating. The steering engine's solenoid valves are operated directly and the rudder can be moved. When such steering failures occur, immediately set the mode switch to NFU and push the NFU lever down to the right or the left while looking at the rudder angle indicator. The rudder moves to the side to which the lever was pushed down. Once the desired rudder angle has been reached, return the lever to neutral position. The rudder movement stops at that rudder angle. Even when the steering stand cannot be used on the bridge, it's possible to steer the rudder by communicating between the bridge and the steering engine room. In this case, solenoid valves of the hydraulic apparatus in the steering engine room are controlled directly. It's important that emergency steering practice drills are carried out regularly. When switching between steering modes, make sure to begin by returning the rudder at the midship position. In a new system, when the mode is switched to auto, automatic steering begins from the current course at that point of time. This needs to be kept firmly in mind. To ensure safe navigation and to respond to emergencies quickly, good communication between the bridge and the steering engine room is extremely important. Daily system checks are recommended, and the entire steering system should be understood by everyone who works with it. Skill improvement and follow-up training are important. When selecting automatic steering, it's necessary to use a setting appropriate to the ship's loading condition, the weather condition, and the sea state. Setting procedures vary between manufacturers. Let's look at some typical settings. The steering system made by Tokyo Keiki offers three kinds of steering mode: manual operation, automatic operation, and non-follow-up. There are two kinds of automatic steering to choose from: PID control and adaptive control, ADPT. In the PID control, it's necessary to adjust for weather conditions, rudder angle, and rate adjustment, and to take into consideration the hull shape, ship type, and loading condition. There are two modes in the adaptive control system. Confined mode offers very accurate course-keeping ability, while open sea mode gives priority to economy during cross-ocean voyages. Both modes can be used in all sea states. Now let's look at Yokogawa's steering system. It has three operational modes: Economy, Precision 1 and Precision 2. Economy is an automatic steering mode designed for energy conservation during cross-ocean voyages. When underway in a rough sea and experiencing excessive yawing, it's better to use Precision 1 instead of Economy mode. Precision 2 is suitable for automatic steering when giving priority to course keeping in congested waters. Yokogawa's system offers a mode for draft data input. Draft mode has three settings: full, middle, and ballast. Should the gyro compass break down, the signal from the magnetic compass can be used in place of the gyro compass azimuth signal. For Tokyo Keiki's system, switch off the repeater power supply. Switch the azimuth input signal from gyro compass to magnetic compass using the switch provided on the steering stand. Next, align the azimuth of the compass card of the steering stand to that of the magnetic compass. For Yokogawa's system, press the EXT button on the control panel to switch the input mode to magnetic compass. With this single operation, signal inputs to all the systems requiring gyro signals are switched to magnetic compass. As a result, the repeaters automatically follow up the magnetic compass. In the event of trouble, the most important first step is to recover proper steering and carry out necessary corrective action. If you understand the system outline, you will be able to respond effectively to any emergency. Both the electromagnetic EM log and the Doppler log are used to measure ship speed. While the EM log measures only the speeds through the water, the Doppler log can measure speeds both through the water and over the ground. The EM log system is composed of a sensor known as the measuring rod, an amplifier, a speed transmitter, and an indicator. The sensor is surrounded by a magnetic field and is attached to the tip of the measuring rod, which protrudes from the ship's bottom into the sea. The relative movement of seawater against the magnetic field generates voltage, which is measured to determine ship speed. The EM log also gives accurate speed indications at slow ahead and astern. The sensor protruding into the sea reduces the influence by the ship's wake and enables highly accurate measurement. However, the sensor is at risk of colliding with obstacles such as driftwood. Therefore, the newest EM logs are flat and the sensor does not protrude from the hull bottom. Shown here is an example of an EM log with an orthogonal bidirectional sensor. It can measure movement speeds fore and aft, port and starboard. At the tip of the device is an electrode, inside of which are a coil and an amplifier that generate a magnetic field. The length of the sensor protruding from the hull bottom varies by model, but normally it's between 7 and 50 millimeters. Since the EM log is used with its sensor exposed to seawater, the hull bottom is fitted with a watertight sea valve. When changing sensors, the sea valve must be handled properly to prevent seawater ingress. Performance of the EM log measuring rod is determined by a ship's hull bottom shape and the rod's installation position. As such, the measuring rod should be adjusted to match the unique characteristics of each ship. Main adjustment items for the EM log are 0-point adjustment, span adjustment, and sensitivity adjustment. 0-point adjustment is conducted when the 0 point of the sensor itself has changed, such as when the sensor is replaced. This adjustment is made when the ship's speed is 0, that is, at anchor. Span adjustment is necessary when log speed is misreported due to fouling of the hull and so on. Sensitivity adjustment is necessary when the measured value changes due to difference in sensor sensitivity, such as when the sensor has been replaced. Remember to read operating manuals before making these adjustments. The EM log does not require daily checks, except when trouble occurs. However, when in dry dock, care must be taken to prevent damage to the sensor. Regular cleaning is necessary to remove scale and oyster shells from the sensor. The Doppler sonar speed log launches a supersonic wave into the sea and uses the reflected signal from suspended matter. It calculates speed by detecting the Doppler shift of the reflected signal. An ambulance exemplifies the Doppler effect. As it approaches, its siren grows in volume, but after it passes by, the siren grows weaker. The Doppler sonar speed log has two modes. One can measure speeds through the water and over the ground, the other through the water only. The EM log can only measure speed through the water, but the Doppler sonar speed log has the ability to measure speeds both through the water and over the ground by switching between the two systems. The Doppler sonar speed log consists of a transducer that launches the supersonic wave, a transmitter-receiver, and a main display. The transducer is located in the bottom of the ship, with oscillators installed at its end. The ultrasound signal is launched in two directions, toward the bow and toward the stern. This is known as the dual beam method. This method has made it possible to significantly reduce the error margin due to hull vibration from rolling and pitching, and the error margin of the speed measurement due to trim changes. Highly accurate speed measurement in rough seas has been achieved. Recently, it's become possible to make the transducer small enough to fit in the bow, where it's less susceptible to the effects of bubbles in the seawater. The main body is composed of the display unit and the operational unit, which switches the display and conducts various measurements. The cursor pad or trackball in the operational unit is used to select the menu. The menu button is used to open the main menu and to halt an operation. Speed through the water is the ship's speed relative to the seawater within 3 meters of the hull bottom. Ground speed can be measured up to a depth of about 200 meters. Note that speed can be measured to an accuracy of 0.1 knots if there is at least 1 meter clearance above the seabed. Because the measured speed is highly accurate, it's effective for speed control when berthing or for making a decision on the timing of anchoring. Due to its nature, however, Doppler sonar speed log accuracy is susceptible to waves during rough weather and bubbles generated when the ship goes astern. Moreover, speed error can be caused by noise interference, etc. Precautions to be taken when in dry dock include turning off the power supply, ensuring the transducer is not lowered onto the docking keel blocks, removing crustaceans, etc., adhering to the surface of the transducer, ensuring that the surface of the transducer is not painted. The GNSS, Global Navigation Satellite System, is a navigation system using the radio waves from a number of satellites. The Navstar system of the United States is one example. Russia's GLONASS and Europe's Galileo are others. Differential GPS, DGPS, has been developed to achieve higher accuracy. The margin of error of the first GPS was about 100 meters. With the DGPS system, the GPS signal is received from a reference point, a point the position of which is known precisely. The error margin is calculated from the position obtained by GPS and the true position. The differential information is transmitted to ships as a correction factor. Based on this correction factor, each ship corrects the position. In Japan, DGPS correction factor information has been supplied by the Japan Coast Guard since 1998 using a radio beacon. A total of 27 coastal beacon stations serve the Japanese archipelago, and their coverage extends about 300 kilometers from shore. Highly accurate positioning is now achieved by DGPS, the accuracy being about 1 meter to 5 meters. The plan is for DGPS stations to be shut down as the accuracy of GPS improves in the years to come. The GPS system is composed of an antenna unit that receives the signal from the satellites, and a processing and display unit that calculates own ship's latitude and longitude from the received signal and displays it on the screen. It displays an accurate location some 90 seconds after the unit has been switched on for the first time. From the second time on, it takes about 12 seconds to display an exact location. A self-test is usually performed when the power supply key is pressed, and the screen displays the information shown on the screen before the power supply was turned off last time. The registration of the destination can be done using numbers from 001 to 999. There are 5 methods for registering a destination. . Own ship's current position. the cursor position on the screen. Registers at MOB or man overboard or the storage position. A present ship position can be made at destination. Specify the distance to travel and the azimuth. Select from the list of destinations. When a person falls into the sea from the ship, immediately press and hold the MOB key for a minimum 3 seconds. This position is saved, and the ship's previously planned destination is abandoned. This enables the ship to return quickly to the MOB position, even in foggy weather or at night. EPIRB and SART are part of the GMDSS, Global Maritime Distress and Safety System. When a ship sinks, its EPIRB is released automatically from the hull and surfaces to begin transmitting an accident report. The signal is received by the COSPAS satellite, and the accident position is calculated automatically. The accident positional data received by the COSPAS SARSAT satellite system is then relayed to an LUT or ground station. A warning is then sent to the appropriate Search and Rescue Coordination Center, and the search and rescue operation by aircraft and/or vessel is launched. A water pressure sensor begins to work at a depth of less than 4 meters, causing the EPIRB to be released from the hull and surface. The EPIRB begins to transmit a distress signal within 50 seconds of its release. Since water pressure is required to trigger the equipment, accidental signals will not be transmitted if the EPIRB is detached from the automatic releasing unit in a dry environment. However, transmission will start if the water sensor terminals are splashed with seawater or touched by a wet hand. When used with a launched lifeboat, the EPIRB unit is attached to the boat by a lanyard and floats on the water's surface. It should be remembered that the distress signal will not be transmitted if the EPIRB unit is lifted clear of the water. It's recommended that maintenance of EPIRB devices be done in a room of windowless steel walls to contain the signal in the event of accidental transmission. When conducting maintenance, make sure that the selector switch on the main body is set to ready, and wipe the entire main body with a piece of soft cloth. Wipe each of the water sensor terminals separately. If the EPIRB is triggered by wiping of both water sensor terminals, you have 50 seconds in which to replace it in the automatic releasing unit before it begins transmitting a distress signal. a distress signal has been transmitted by mistake, corrective measures must be taken immediately. First, stop transmitting the distress signal. Second, report to the appropriate search and rescue coordination center. These are determined by vessel nationality. In the case of Japanese ships, a report should be made to the Japan Coast Guard. All emergency transmissions carry the information as shown here. The selector switch has three positions: ready, test, and on. In normal operation, the switch is always set to the ready position. In this position, the EPIRB is released and begins transmitting a distress signal automatically after its water sensor detects water. Test mode is used to check EPIRB functions. It can be set without breaking the stopper pin. On mode is designed to activate the EPIRB and purposely transmit a distress signal. Break and remove the stopper pin to set the EPIRB to on mode. The unit will cease transmitting when it's removed from the water and the switch is returned to the ready mode, turning off the power supply. It's necessary to test the EPIRB once a week to confirm that it works properly. Only one transmission burst is permitted during the transmission test. Never attempt to repeat the test. When conducting the test, make sure the selector switch is set to and held in the test position, and that the EPIRB remains in the automatic releasing unit. When set to the test position, the battery voltage is checked. The battery is considered normal if the orange LED and the yellow LED go off after lighting up for 4 seconds. If the orange LED and the yellow LED go off after flickering for 4 seconds at an interval of 0.1 seconds, the battery is running down. Next, conduct a transmission check. The transmitter is normal if the yellow and red LEDs light up for approximately 0.4 seconds. If only the yellow LED lights up for approximately 0.4 seconds, however, the unit has failed to transmit and should be replaced. When none of the LEDs light up, the transmitter is malfunctioning. The indicator lamp is normal if it flashes at an interval of 2.6 seconds. Cease holding and the test mode will finish, automatically returning the selector switch to ready position. Because the tests consume very little of the battery's power, you are encouraged to carry out a transmission check every week. When an X-band radar signal from the search ship is received, the SART, Search and Rescue Radar Transponder, triggers the search radar to transmit a distress burst consisting of 12 dots in the same X-band. SART uses a blinking pilot lamp and a buzzer to alert you that a rescue ship is approaching. The SART signal can be detected by rescue ships at a distance of about 10 nautical miles, and by aircraft at a distance of about 30 nautical miles. Ships and/or seafarers in distress are often caught in rough seas, making it difficult to detect lifeboats or life rafts merely by sight or radar. SART is valuable because it allows easy detection of the accident site using a radar display. EPIRB distress signals can be received anywhere in the world via the Cosbus SARSAT satellite system. SART is used by other ships in the area to approach shipwrecked people awaiting rescue. A SART unit is usually installed on a bracket mount inboard the bridge. From here it can be quickly taken to a lifeboat or life raft in an emergency. Upon receiving a radar signal from a search ship, the SART's display is switched on and begins to respond using a flickering red LED or sounding a buzzer. The red LED flickers intermittently in response to the search radar's beam. On the search radar screen, a line of 12 dots will display the direction of the active SART. When operating a SART on board own ship or in the lifeboat, SART should be fixed with the radome up in a holder or lashed to a handrail with a rope. When using the SART, remember to switch off own ship's radar. This is necessary because the SART might respond to the high signal level of own ship's radar, causing the indicator LED to light up. Detection by the search radar will be unknown, while sapping the SART battery of power. Continued use of own ship's radar may even cause the SART to fail. When used in a life raft or lifeboat, it must be removed from its location on the ship and switched on after being brought on board the raft or boat. In a lifeboat, there's an area where the SART can be installed on the ceiling. Remove the SART mounting unit's bottom plate, pull the string to remove the SART from the hook, then push the upper part of the SART out of the boat. In a life raft, the SART should be located as high above sea level as possible, and in such a position that the red LED light can be seen from the cabin. The SART signal is received from the radome's horizontal direction, so make sure that objects such as radar reflectors are not obstructing the upper part of SART. The SART battery is capable of 96 hours of uninterrupted use, so its power should not be switched off until rescue is complete. When own ship has become a search vessel, carry out a search and rescue operation with the radar range set to 12 miles or greater. This is necessary because the SART signal appears as a 12-dot line extending out to the 8 nautical mile range, and the radar visibility range is about 10 nautical miles. To facilitate reception of a SART signal, the operator on the search ship should set the sensitivity time control, STC, and fast time constant, FTC, to 0. Once a SART signal has been found, let the rescue ship proceed toward the dot of the line closest to own ship. As the rescue ship approaches the SART, its signal will strengthen, appearing as multiple arcs in the radar's side lobes. As the rescue ship draws closer, concentric circles of multiple dots begin to appear on the radar screen. At this point, it's possible to clearly identify the SART signal by adjusting the radar's gain back to the dotted line display. The VDR, Voyage Data Recorder, is referred to as the black box of the ship. Combining a flight recorder and a voice recorder, it's similar in function to those found on aircraft. In the wake of a marine accident, the VDR is collected from the ship. The recorded navigational information, such as ship speed, rudder and engine settings, verbal communication on the bridge, and VHF voice communication, is used to examine and identify the accident's cause. If no radar information can be input, the AIS data are input instead. VDR system is composed of four main parts: a data collection unit, DCU, for data recording, with a built-in HDD, a data recording unit, DRU, capable of recording 12 hours of data on its built-in memory, a remote alarm panel, RAP, and a microphone. Data collected by the DCU are recorded in the built-in memory of the DRU and at the same time in the backup HDD within the DCU. The DRU records a 12-hour loop of data. This loop is continually updated with fresh incoming information. UTC time is used throughout the system. The memory containing the recorded data is kept in a protective capsule. The capsule can survive hydrostatic pressure equivalent to 6,000 meters of water depth. It transmits its position using an underwater sound beacon for a period of 30 days. The VDR system remains switched on and continues to record data until the ship's power supply fails. As such, there is the risk that data recorded at the time of accident may be overwritten and updated by new data. Access to the DCU is simple, but is limited to those in authority with a necessary key. To start the unit, the following switches must be engaged sequentially on the power supply control panel: the AC supply main switch, the DC supply main switch, and the battery backup switch. When normal LEDs on the power control panel and on the RAP light up, data recording begins automatically. When evacuating the ship due to a marine accident, try your best to remove the HDD in the DCU. The procedures for removing the HDD are: first, press and hold the save button on the RAP. The yellow LED will blink. Wait until the blinking stops and the light is constant. Use the key to open the door of the DCU. Turn off the power supply switches in the order of battery, DC, and AC. Remove the latch of the HDD holder. Take out the HDD. Detach the cable connected to the HDD. The echo sounder is used to measure the depth of water under the ship's hull. Miscalculating own ship's draft and the depth of the sea area being navigated could result in a serious accident, such as grounding. Without doubt, this knowledge is of vital importance for safe navigation. The speed of sound in seawater is about 1,500 meters per second. The echo sounder determines water depth by measuring the time taken for a transmitted sound wave to travel to the seabed and return. It's possible to measure depths of up to 200 meters or so using an echo sounder while underway. The operating panel can accommodate settings such as ship's draft value input, measurement range, and sensitivity. There are 5 different echo sounder display modes. Nav, or navigation mode, is used to measure the depth from the transducer to the seabed. DBS, or depth mode, calculates the depth from sea surface to the seabed. History, or seabed history mode, displays the seabed profile and normal measured depth. The 2 other modes are logbook mode and OS data, or own ship data mode. A new function records and reproduces the ship's position and the depth of water under it for the past 24 hours, all without need for paper. Issuing a warning when water depth is below a preset figure is another function. Precautions to take when the ship is in dry dock are as follows. Turn off the echo sounder's power supply. Ensure that the transducer is not lowered onto the docking keel blocks. Remove crustaceans, etc., adhering to the surface of the transducer. Do not paint the surface of the transducer. In this video, we've seen typical examples of modern navigational instruments. Recent technical advances, such as the increased use of satellite communication, GPS, and digitalization of systems, have led to many remarkable high-performance nautical instruments. However, no instrument is perfect. We must always be on the lookout for trouble. Therefore, we must always keep up with technological advances and strive to familiarize ourselves with new equipment and its uses. We encourage you to properly understand the roles, functions, and characteristics of navigational instruments so that you can use them to your advantage and navigate safely.